Hello everyone. This presentation on machine learning enabled high frequency, low power digital design implementation and advanced process nodes is a joint work by me and Vishal at Synopsys. The outline of my talk is as follows. First, I will provide background and motivation, followed by previous work. Next, I present problem formulation and our methodology. Thereafter, I present our experimental setup and results, and I conclude the talk with a summary and future work. A very quick introduction to graph-based static timing analysis. Let's say the path under consideration is highlighted in blue. In GBA STA, the merge nodes, which are U1Z, U2ZN, and U3ZN, they propagate the worst slew at the input pins. So therefore, the worst slew at each of the input pins get propagated, and at the endpoint, which is FF1, FF2D, we get a transition of 71 picoseconds. On the other hand, path-based analysis, STA, propagates the actual transition at the merge nodes. Therefore, at each of the merge nodes, the path input slew gets propagated, and at the endpoint, we get a transition of 61 picoseconds. As a result, you see that a pessimism has been reduced from the GBA STA. This also leads to improvement in slack or slack pessimism reduction at the endpoints. So what are the opportunities to perform PB analysis in digital implementation? There is a huge push to achieve sign-off quality, timing, and power for best-in-class power, performance, and area, or PPA. At the same time, the GBA and PBA gap at advanced nodes can be very large. For example, the picture on the right-hand side shows PBA slack in the x-axis and the GBA slack in the y-axis. So we can see that there can be a delta of about 78 picoseconds, which is around 4 to 5 stages of logic at 7 nanometer. Implementation has a rich set of optimization moves as compared to ECO sign-off. For example, advanced logic restructuring, layer promotion, NDR with reroute and rebuffering, flexible clock and data, legalization, and ECO routing aware optimization. So if we can perform PB analysis and implementation, we have the chance to prevent over-design, that is area and power loss. But this is fraught with challenges. For example, true PB analysis requires exponential path tracing. This leads to massive increase in memory and runtime. The overhead can be up to 50% of GBA runtime, as reported in various published articles in the past. True PB exhaustive makes turnaround time, or TAT, infeasible on large-scale designs that have 1 to 10 million instances. PBA path is an alternative, which essentially retimes the worst GBA path using PB analysis. And practical considerations can limit design companies to analyze the top K paths, for example, the top 10,000 paths. Incremental STA using PBA in implementation flows is very tricky because there has to be a fine balance of runtime versus correct analysis. Now I review previous works. Previous works can be broadly classified into two categories. The first category develops heuristics to improve the raw PB analysis runtime. Bai et al. They propose PBA path, the top K path analysis. Gupta et al. Propose IPBA, which is an infinite depth parallel traversal of timing graph using breadth first search, and they speed up stage-wise computation. Shamsukha et al. They perform selective PB analysis based on statistical and non-statistical path characteristics. Rickson et al. They propose a thresholding mechanism while merging timing values. The second category of works are relating to ML-based heuristics. Wang and Wong create a task graph and use MapReduce to massively scale PBA analysis. Kang et al. They predict PBA timing using GBA features using a bigram approach to capture path timing features. This is the closest to our work. However, the feature extraction time is pretty large in this work and therefore can be challenging to deploy in implementation flows. The key contributions of our work are as follows. Ours is the first application of ML paradigm to optimize post-routed designs using predicted PBA slack using a ML augmented GBA flow. We proposed on-the-fly training methodology and several insights on how to choose features and a modeling algorithm for our prediction task. We apply several novel engineering strategies on model guidance for delay, area, and power recovery to reduce GBA flow over design. We integrate our methodology in a commercial EDA tool and present non-trivial PPA gains on real industrial designs from 5 nanometer to 16 nanometer. Our experimental results have a moderate runtime overhead of around 3% with respect to a GBA baseline flow, and we achieve up to 11.7% reduction in leakage power and 1.16% reduction in total power. Although 1% reduction in total power seems a very small number, but actually if we consider that baseline GBA flows are running state-of-the-art power algorithms, in perspective of that, this is a very large number because companies are really vying to save every 1 milliwatt, and in that light, 1% total power savings is a huge number. Now we present our formulation of a problem. We design a ML-based predictor of PBA slack given GBA features. So therefore, we extract features where the timer is configured in the GBA analysis mode, and then we create an ML model which predicts slack as if the timer were configured in the PBA analysis mode. We predict multi-corner, multi-mode PBA slack across all critical paths, and we create separate models for delay and recovery. The reason for that is sometimes the PBA labels at the delay and the recovery stage, they have a completely different distribution. So therefore, the model trained for delay does not generalize well for recovery. We integrate the models in a commercial post-route optimization flow. An example of a commercial optimization flow is shown in the flowchart on the right, where a routed netlist is taken and then we perform several electrical fixes such as logical DRC SI, and then we perform setup and hold fixing using clock and data path optimization techniques. Once delay is stabilized, next area and power recovery is performed again on clock and data paths, and finally the netlist is legalized and ECO routed. We integrate our ML model in this kind of a flow, and I will explain how this is done subsequently. We adjust GBA timing on critical paths based on our model's predictions. Some words about our on-the-fly training. This is a very key innovation in our work because it enables very low runtime overhead and prevents two-pass flow even though our model is supervised learning. So we eliminate need for two-pass training and inference flow requirements because it causes deployment challenges at customers due to data management issues. We develop a one-pass flow where the model is trained when large changes to the netlist occurs that shifts PBA labels. The model is inferred and refreshed at strategic points in the optimization flow during delay, area, and power recovery. Now this requires a lightweight and accurate training methodology. We require low overhead of feature extraction, fast and parallel algorithms for model training, and for this project, we placed a constraint that the runtime overhead should be less than 5% of our baseline GBA flow. We also need to come up with a cost function that accurately predicts the model's design PPA. Here is a list of our features. We divide them into various categories, and I specify the number of features in each category and the justification. So for example, we have 4 features that describe the physical context, such as the start point and the end point locations, and the Y length in the X direction and the Y direction. So this helps discriminate path layouts. We have 4 features belonging to the logical context, such as number of stages in the critical path, max fan out, etc. They indicate the extent of the GBA and PBA divergence. Timing context has 9 features such as start point cap, slew, endpoint cap, slew, etc. These help again discriminate between path timing characteristics. Physical constraints has 2 features which are don't touch and number of size only cells. Again, they indicate the extent of GBA and PBA divergence. Timing constraint has 4 features such as number of max strand violators on the critical path, endpoint arrival required, and the scenario. Again, this category of features help discriminate types of paths as well as indicate the extent of GBA and PBA divergence. This picture over here shows our feature importances. The black line shows the variation in the ensemble of models that we create. We see that the top 4 features are the endpoint arrival required as expected because we are predicting slack. The start point slew, the start point cap, because the clock path plays a very important role, especially if there is variation and CRPR effects. The rest of the features are essentially useful for fitting residuals. So machine learning algorithm is shown by this equation over here, where we're predicting PBA timing using GBA features, and we are learning some model parameters theta. So we use a gradient boosted random forest regressor because these are fast to train and accurate, and they are easy to debug outliers as compared to deep neural networks or other complex models. The hyperparameters are intuitive and easy to tune and deploy. So we bootstrap the algorithm using 50 to 70% of the training data. At each node, we randomly sample 50 to 70% of features. We select the feature that has the largest information gain, and once the tree is built, we prune the trees that violate the max depth or the min number of child nodes criteria. Our objective is to minimize root mean squared error between GBA and PBA slack, because this is an accurate indicator of design TNS. Here is an example of one of the trees that our algorithm builds. This is an example of how we implement the ML augmented GBA flow. So on the left hand side is a baseline GBA flow that I described a few slides back. So what we do is, during delay fixing, we train a delay model, and during the various steps of delay fixing, the model is inferred and adjustments are applied. Similarly, during area and power recovery, we train another model, and then we incrementally infer them during optimization. Note that the optimization mega command can be run many times, and the decision to create 2 versus 1 model is automatic, because if the algorithm decides that there is no shift in PBA labels or dramatic shift in PBA labels, it can just do with 1 model. So what we see is that from the second route opt onwards, we can just train 1 model and use it to infer on all other subsequent route ops. Here is our experimental setup. Our modeling is implemented in C++ and Python. We do an 80-20 train test split. Model is trained using PBA path labels, essentially for fast turnaround time, but our methodology also works with PBA exhaustive. We integrate post-route optimization flow of a commercial EDA tool. The experiments are run on 21 industrial designs on Intel Xeon 16 core 2.6 GHz machine. This table shows various characteristics of our design. Due to NDA considerations, we cannot provide design names, so that's why we have abstracted the design names using some kind of descriptive category. So our designs can be either total power or leakage power based. This picture shows how accurate our model is. We plot the ratio of the root mean squared error, difference between GB and true PBA, and the root mean square error difference between predicted PBA and true PBA. As you see that, in certain cases we can improve the RMSE ratio by up to 30x. Similarly, if we study the model for recovery, we see that we achieve pretty significant RMSE ratio improvements. So impact on post-route optimization. So we know that PBA reduces delay pessimism. That means we expect fewer instances to be selected during delay fixing as compared to GB, and more instances to be selected during area and power recovery as compared to GBA. And we kind of see those trends in these designs. As expected, runtime reduces because we work on fewer instances during delay optimization. And the reverse trend is seen during area power recovery. And as expected, we burn more runtime in area power optimization. So on this particular design, D5C, the GBA PBA gap is very small. That's the reason we don't see very large improvements. This is the overall result of our optimization. So the gamma denotes designs which are leakage power, and we normalize the total negative slack with respect to path delay for unbiased comparisons. As expected, ML augmented GBA flow improves area and power. As we see over here, we get up to 1% area, 1% total power, and up to 11.7% leakage power. However, we do have some TNS degradations, and we studied the causes for this, and these are mainly due to inaccuracies due to model reuse, because as I mentioned, from the second route opt onwards, we can do with one model, but still, sometimes on certain designs there can be large shift in PBA labels, and our threshold for retraining the model is not high enough. That's why we don't train the second model, and we incur errors in TNS or degradation in TNS. And the other reason is basically, since we train using PBA path, we incur some error because the final timing is can shift, because the worst GBA path may or may not be the worst PBA path after legalization and ECO route. The statistics of overall PPA and runtime improvement are shown in this table over here. As expected, area leakage and dynamic power are largely improved, as shown by the green colored mean and average. And pretty much of all the 21 designs, most of the designs we have, around 80% of the designs we have wins. Now, the bottom table shows other metrics where, TNS, as I mentioned, we have some losses. But overall, if we look at it, right, the wins are greater than 40% of the times. Summary and future work. So PP optimization at advanced process nodes is very challenging in traditional GBA-based implementation flows. We demonstrate a fast and accurate ML-enabled methodology to learn PBA timing and apply in an ML-augmented post-route optimization GBA flow. Our detailed insights on feature engineering model selection hopefully helps other ML projects in digital implementation space. We achieve up to 11.7% leakage power and 1.16% total power reduction across multiple industrial designs from top semiconductor companies spanning from 16 nanometer down to 5 nanometer. Our ongoing works are to improve timing outliers, the TNS outliers, and then also to develop ML augmented pre-route GBA flows. Thank you so much for this opportunity.